This is part 2 of the lecture covering non-constant acceleration. In part 1 of the lecture, I took you through the basics of how you calculate the derivative of a polynomial. Here I'm going to take you through the basics of the reverse process, which is known as integration. As I go through this process, like I did in part 1, I'm going to skip over the theory that is necessary to understand exactly what it is that you're about to see. You're going to get that theory, however, in your calculus class anyway. Instead, what we're concerned with here is just technique. For example, how do you evaluate the integral associated with a polynomial? Okay, now from a purely mathematical standpoint, integration is concerned with finding areas underneath a curve. So for example, let's say that I do draw out a polynomial in the following way. Okay, so I have some sort of smooth curve like so. And now let me pick 2 points here along the x-axis. This point right here is typically labeled as A. This point here is labeled as B. Okay, notice immediately that due to the curvature here associated with this polynomial, we can't use simple geometrical techniques in order to find the area here that is constrained between points A and B. The ancient Greeks, for example, tried to formulate a means of finding the true area underneath the curve on a graph such as this. They never were able to make a true calculation of that area. Instead, they could only come up with an estimate. Now, in order to find the true area here underneath the curve, we actually do begin with an estimate. What I'm going to do is I'm going to fill the space here between points A and B with a series of rectangles. All of these rectangles, I'm going to draw them below the curve itself. They're called inscribed for that reason. And all of these rectangles have the same width. That width is going to be referred to as delta x. So now let me draw out these rectangles like so. Okay, here, and as I draw these rectangles, regardless of the poor quality of my artwork here, keep in mind that they all do in fact have the same width, like so. So let's pick one of the rectangles here and indicate the width here as delta x. Okay, I'm going to begin by finding the area of this single rectangle. This rectangle here we're going to refer to as the kth rectangle. So how do you find the area of that single rectangle? Well, it's just going to be base times height. So the base is the width delta x, but what about the height? Well, the height of this rectangle is the value of the red function itself right here at this value. This value here is referred to as f of x sub k, like so. So x sub k is just referring to the variable x right here at this point on the graph. And now the area of that single rectangle is just base times height. That's the following. Okay, typically we write it like this. Like so. Okay, now that's just the area of one rectangle. What do I do to get the area of all of the rectangles? Well, we calculate the area of all of the rectangles very simply and then add them all together. So that's then written in the following way. Okay, so area of all of the rectangles. What we're going to do is we're going to sum over the k rectangles. This is the summation symbol, and then think of this as k equals 1, k equals 2, k equals 3, k equals 4, and so on. And then what we do is we take their heights and multiply them by their widths. Once again, the widths are all the same. Now, does this quantity here truly give us the area underneath the curve? No, not quite. It's only an estimate. We miss, for example, a little bit of area here, 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 and so on, like so. So then therefore, what could I do to these rectangles to get a truer and truer calculation, if you will, of the area underneath the curve? Well, I can do 2 things with them. Number 1, I can make the widths of the rectangles increasingly smaller and smaller. But when I do that, I then have to increase the number of rectangles that are drawn underneath the curve. How do you write this out mathematically? I'm not going to draw it. Well, the way that you write this out mathematically, very simply, is to take a limit. Take a limit as the width of the rectangle's delta x becomes infinitesimally small. This will then give us the true area underneath the curve. That's written like this. Like so, this quantity here. Once again, now think of the rectangles as having an infinitesimally small width. This then gives us the true area underneath the curve. This quantity here is known as the definite integral, but it's at this point here in mathematics, you're going to see a change in notation. Okay, we rewrite this quantity in the following way. Okay, first of all, we replace the summation symbol with what is known as the integral sign. That's written like this. Okay, and then we have points A and B on the graph above. These are known as the limits of integration. Point A is called the lower limit of integration, and it's written right here. Point B is known as the upper limit of integration, and it's written here. Okay, and then next we have the height of all of the rectangles. Well, the height of all of the rectangles is just the function itself, because now remember that all of the rectangles are infinitesimally small. That's this quantity right here. And by the way, this is known as the integrand. Okay, and then we have the infinitesimally small widths of the rectangles. We now write that as dx. So this quantity right here mathematically means the exact same thing as this. It's at this point here in a calculus class where you would pause. And you would pause, and over the course of probably a couple of weeks, you would be introduced to a couple of theorems. These theorems give you the punchline, if you will, on how you evaluate an integral. I'm going to skip over those theorems and just go straight to the punchline. In order to evaluate an integral, you have to find a new function. Okay, let me describe in terms of notation what that new function is, and then I'll take you through the process for polynomials. First of all, let's write out the following. Like so. The punchline of the theorems that I'm not describing here is that evaluating an integral turns out to be the reverse of calculating a derivative. What we have to do to evaluate an integral is we have to find a new function. This new function is known as the antiderivative of the original function f of x. And then once we have that new function, we then do the following. In terms of notation, this vertical line here means evaluated between. What we do is we take this new function and we plug into that function, first of all, the upper limit of integration. That's this quantity here, and we get some number. And then we subtract from that the following. What we then do is we take the lower limit of integration and plug that into the function to get this number here. And then the difference between the two, this then gives us a true area underneath the curve. So the punchline of the theorems that I'm not taking you through here is that the process of integration turns out to just be the reverse of differentiation. Okay, now for simple polynomials, how do you find this new function called the antiderivative? It's the reverse process of differentiation, and it's the following. Okay, let me do some erasing. Okay, so let's say that we have a simple polynomial like so. There is a restriction, however, for this polynomial. Okay, the process that you're about to see cannot be done if n is equal to -1. If n is equal to -1, then something else happens, and you'll see that in calculus class anyway. So for now, n cannot be -1. However, it can be anything else. It could be an integer, it could be a positive number, it could be a negative number, it could be a fraction, it could be a decimal, etc., etc. The only restriction is that it cannot be equal to -1. At any rate, however, in order to find the antiderivative, we now do the following. We take the value of the exponent and we increase it by 1, like so. And then we take this new exponent and we place it in the denominator of this quantity, like so. This right here is the antiderivative of a polynomial. What I did was the reverse of differentiation. Here's a way in which we can check ourselves. The derivative of this quantity should be equal to the original function. So let's see if it is. Okay, so recall from part 1 of this lecture how you find the derivative of a polynomial. That is, you take the value of the exponent and you bring it down in front, like so. And then you take the value of the exponent and you lower it by 1, like so. If I now simplify, I end up like so with the original function. So then therefore, this quantity here is the reverse process of differentiation. This guy here is known as the antiderivative. So now let me show you how to apply this for a couple of simple polynomials. Okay, so let's begin with just a constant, like so. And let's graph it out here, and specifically we're going to say our lower limit of integration is 0 and our upper limit of integration is 1. And then right here is the value of the function itself, the constant c. Okay, now this is a problem that we can actually tackle geometrically, because all that I've drawn out here, like so, in this space, is a rectangle. So then therefore the area of that rectangle is just base times height. Notice that the base is just equal to 1 multiplied by the height c. So then therefore we should end up with c as the answer. Okay, now let's go ahead and find that answer by setting up and evaluating the following integral. Okay, first of all, we now write the function. In terms of the shortcut, however, that I wrote earlier, think of the constant c as the same thing as c times x to the 0th power, like so, because x to the 0th is 1 anyway. And then we have our infinitesimally small value of dx, like so. Okay, now we then find the antiderivative by doing the following. We now take the value of the exponent and we increase it by 1, like so. And then we take that new exponent and we place it in the denominator. This right here is the antiderivative. And then we evaluate this, once again, that's what this vertical line means, between 0 and 1. Like so. Okay, now as I did this, you may be saying to yourself, okay, well, what happened to this little guy right here? And all of a sudden it just disappeared. Well, remember that this and this is all just notation. The thing that you want to concentrate on is this, the integrand, the function itself. And we then find the antiderivative of that function right here. And then we evaluate it between 0 and 1. So now what we do is we take the upper limit of integration, 1, and we plug that into the function first. And when we do, we just end up with this. And then subtract from that the lower limit of integration plugged into the function, and we then just end up with this. And then therefore the answer is c, like so. Hey, here's another simple example. Let's do something that's linear. Okay, so something that's linear, I'll write it as cx to the first power. And this is just going to be a line with a slope of c. Okay, once again, let's just go between 0 and 1. Like so. Okay, now this space right here, that's a triangle. So then therefore, geometrically, we can find the area of a triangle is 1/2 base times height. Okay, now the height of the triangle, by the way, is the value of the function here when x is equal to 1. When x is equal to 1, the value of the function itself is just c, like so. So if you do here 1/2 base times height, it's 1/2 times 1 and then multiplied by c. We should end up with 1/2 c as the answer. Let's see if it is. Okay, so now we set up our integral, like so. And then we now find the antiderivative here of our function. So take the value of the exponent and increase it by 1. And then take the new value of that exponent, place it in the denominator, and then we evaluate between 0 and 1. So take the 1 and plug it into the function first, and you just get 1/2 c when you do. You then subtract from that what happens when you take 0 and plug that into the function. This then ends up being -0. So then therefore the answer is 1/2 c. So once you get the hang of it, finding the integral for a polynomial, if you just think of it in terms of pure technique, is actually really easy to do. Let me finish here with just one more example. Okay, let's say we have a quadratic. So this right here is just a parabola that opens upwards with the vertex at the origin. Like so. And then we'll once again go between 0 and 1. And then once again, what we have to find here is the area underneath the curve. Notice that even with something as very simple as a parabola, we can't use any sort of geometrical technique in order to find this area. The only way in which we can find this area is by integrating. Okay, so let's go ahead and do so. And now what we do is we take our value of the exponent here and increase it by 1. Take that new exponent, place it in the denominator, and then we evaluate between 0 and 1. Plug the 1 in first, and this then ends up being 1/3 c. Subtract from that the 0 plugged in like so, and then therefore the answer just ends up being 1/3 c, like so. So basically what you do in the second half of a calculus class is you learn the theory behind integration. Of course, that's what I skipped over here. And then you learn how to evaluate the integration associated with various functions. And that basically right there is a 2-semester course in calculus. It's in the 3rd semester, by the way, called multivariable calculus, that you begin to apply what it is that you learned in the first 2 semesters. But basically the first 2 semesters of calculus class is learning how to calculate derivatives of various functions and then learning how to calculate integrals of various functions. Okay, I'm going to go ahead and finish this part here of this series of lectures on non-constant acceleration. And the next part, then we'll begin to specifically apply this to motion.